right, make sure I've got this set up. Yep, okay, so we'll start with part 4, which is exponential and logarithmic equations. And this is where we've been going with the first 3 sections. We wanted to be able to do this. So we're going to apply the one-to-one property to solve equations of both the logarithmic and the exponential type. And the one-to-one property basically says this. If you've got b to the x, and that's equal to b to the y, as long as these bases match and are valid exponential bases. So if you have the same base, then the exponents must be equal. So b to the x equals b to the y means x equals y. This is the one-to-one property of exponentials and logs. So the log version of it looks like this. Log base b of x equal to log base b of y means also that x equals y. So those are the two. And again, it must be the case that it has the same base, and that base is a valid logarithmic base. Remember, that has to be positive and not equal to 1. All right, questions about this? It might seem pretty intuitive, but in mathematics, they don't trust intuition. You need a rigorous proof for anything, any claim you make. So there's rigorous proofs for this. So let's solve one. In order to solve it using the one-to-one property, I need to rewrite something as the same base. So here I have 4 to the x plus 2 equal to 16 to the x minus 3. So if I look at these two bases, I need to think of a way to write one as a power of the other. And in this case, a pretty obvious solution presents itself. Does everybody see why that's the case? 16 is 4 squared. So one more step, though, before I can do anything with that one-to-one property. I need to be careful with the power of a power rule. When I multiply these two together, I should consider that binomial one number with parentheses like so. Now we can use the one-to-one property, which allows us to set those exponents equal to each other. So I get x plus 2 equals 2x minus 6. Subtract x, add 6, 8 equals x. So that's the one-to-one property of exponentials. As always, stop me if you got a question. Gonna take roll real quick. All right, so Colby? Here. Bethany is not. Macy? Here. Caitlin is not. Mackenzie? Here. Allie? Here. Clay? Here. Riley? Here. And that's it. All right. So let's do one that involves a.
Can you go back to the last one just for a second?
Sure. Yeah, don't let me get ahead of you.
So can you explain the last step again? Because whenever I get 12 equals negative 2x, which is 2x equals negative 6.
So I've set the two exponents equal to each other. And in the case on the right side, I have to distribute this 2. So that's where the 2x minus 6 comes from. So once I'm here, I'm going to subtract away x from both sides. And then I'm going to add 6 to both sides. 2 plus 6 is 8. 2x plus a negative x is x. So I'm not sure where 12 would come in.
Oh, sorry. Never mind. I see where my thinking was messed up. I was just looking at it.
Maybe multiplied here? Or?
Yeah.
Okay. But yeah, that would be adding. All right. So let's look at one where the solution is not quite so obvious as to how to rewrite the basis. Sometimes you have to rewrite both bases. And this is such a case, I think. So I'm going to write this as 3 to the negative 1. And this as 3 to the negative 4. And at this point, I need to use the power of a power rule. And from here, I can apply that one-to-one property again. So that's negative n equals negative 8/3, or n equals 8/3. This step right here, the second step, is the one that's going to challenge most of you. Because you have to know some things about exponentials, know some common powers of all the lower values. All right. Questions? Okay. So here's one for you, quickly if you can. Try to solve this for me. You get stuck, let me know, and I'll come around and help you. All right, Riley, what's the answer to this one?
X equals 2.
Very good. So the key here is rewriting 25 as 5 squared. And then after that, you would take power of power and then use the one-to-one property. So it's pretty straightforward. This is the step, again, that would probably challenge people the most. Good job. All right, one-to-one property of logarithms works the same way as we have previously discussed. So we want to solve 2 times the natural log of x equals 18. So that's a case where we would divide both sides by 2, and the natural log of x equals 9. So the only way I can solve this problem is to rescue the x from the argument of the logarithm. I want you to pay careful attention here because it's probably the first time you've seen me do this. I'm going to use a legitimate algebraic step, that is to exponentiate both sides. So I'm going to take both sides as the exponent of the natural log's base. In other words, e to the ln x equals e to the 9th. That is a legitimate algebraic step. It's called exponentiation. And it undoes the logarithm. It is the yin to the logarithm's yang. So e to the ln x, what power, or if I take e to the power I put on e to get x, that just becomes x e to the 9th. And they want us to approximate this to the nearest hundredth. So that's going to require a calculator, of course. (8103.08) to the nearest hundredth. So an exciting day for you guys. You saw me exponentiate for the first time and life was discovered on Venus. Which of those is more important? I don't know. So you'll notice the algebra here is not really challenging. But because we're dealing with a whole new algebraic mechanism, that part's going to be difficult for you to intuit. So a lot of you would get to hear and say, like, what the heck do I do now? Well, when you have a variable as the argument of a logarithm, the answer is always to exponentiate, to take as the exponent of that logarithmic base. Eventually, that will become instinctual. All right, 7 minus 3 times the log of 10x equals 13. Just going to do some pretty standard algebra here. So I'm going to subtract 7, and I get negative 3 times the log of 10x equals 6. I'm going to divide away negative 3. So I get the log of 10x equals negative 2. Now don't get it twisted. The logarithm may not accept a negative value as its input, but a negative value for the output is just fine. So you remember we studied a lot of logarithms that had a negative output, so this is perfectly okay. Once again, we have the variable trapped in the argument of a logarithm. So once again, I must exponentiate. But this time, e is not the logical choice. The base of this logarithm is 10. And so I take both sides as a power of 10. It's called exponentiation. And so this becomes 10x. I divide both sides by 10. I'll get this value. Or 1 over 1,000 if you prefer. Make sure and ask me a question if you have it, or if you need a general recap. Okay, sure. Glad you asked, because you're probably not the only one that could benefit. So once again, when we're solving a logarithmic equation, as in this case, we'll do whatever algebraic steps are necessary to isolate the logarithmic term. So the first few things I did were to get the log by itself. Once we have the log by itself, the key is to exponentiate. In other words, take both sides of the equation as the exponent of that logarithm's base. So I knew this was base 10. That's why I chose 10 for my base, and then used so this is the one-to-one property again of exponentiation, used in reverse from before. And this is pretty straightforward afterwards. But again, this is the step that will probably confound you the most in this case. Good question. Other questions? All right. So, a little more funky example here. Log base 5 of x to the 4th power equals 20. So there's a couple approaches I can take, but I think probably we're going to lose some solutions if we're not careful. So if I bring this 4 out as a coefficient using the power property and then divide both sides by 4, I'm going to lose a couple solutions that way. So anyway, what I'll do instead is take both sides as a power of 5. So what I'm going to get is x to the 4th equals 5 to the 20th, which I'll leave in that form because that's going to be a monstrous value. And then I'll say x equals plus or minus the 4th root of 5 to the 20th. So when I take an even indexed root, I must consider both the positive and the negative. So that negative is what we would have lost if we had used the power property first. So x equals plus or minus 5 to the 20 over 4, which is plus or minus 5 to the 5th power. So some more manageable value. 3125. And we'll just check our answers to make sure they work. So the log of 3125 to the 4th divided by the log of 5. That's 20, so that one worked. And now we need to test the negative. Oh, it says non-real, but it shouldn't be the case. Oh, I need to put it in parentheses. Okay. All right. Yep, there we go. So in both cases, these are solutions. You would have lost the negative solution if you had used the power property at first. So something to be careful of. I probably would only take off a point or two if you did that on a quiz, but still a point worth having. Questions about this one? All right. So here's one for you. See if you can use those same processes to solve this logarithmic equation. Remember also that odd indexes don't have sign ambiguity. In other words, there's no plus minus when you take a third root. If you get stuck, let me know. Well, yes, however, now the way you wrote this is a little strange. Yeah, so it should be as a superscript. And that's probably a little subtle in the way you wrote it here. But when you exponentiate both sides, both become exponents.
Okay.
So even this funky expression is just an exponent.
Okay.
Now you're at a point where you can
Okay.
probably solve it. Yes.
I'm trying to check it.
Show you how you do that. So it's 2 times a log of x cubed. So that's the argument, and this would be a cubed. Divided by the log of the base, using the change of base rule. That should be 18. So the answer works.
Thank you.
You're welcome. Then we'll divide both sides by 2. And if you're taking both sides as the next one, then it'd be 2 to the right. Be careful not skipping steps, especially with these problems. You notice I don't do it. That's because I want to be expository, first of all. In other words, teach the material. Second of all, it's because it's very likely to cause an error when you skip steps. Okay, so Clay, what'd you get here?
We got x equals positive. It's either positive or negative 8 or just 8.
Just
Right.
positive 8 in this
Okay.
case. So remember, when you have an even index, you have sign ambiguity. But when you have an odd index, which is you will in this case on the last step, you're taking the third root. There's no sign ambiguity.
Oh, okay. That's what
There's no plus or minus. So third roots are either positive or negative, not both. So, but good job. You did find the right answer. So your algebra was sound. So now let's solve a more complicated one. These are kind of fun because we have to use those laws of logs from yesterday. So before we can apply the one-to-one property of logarithms, we need to condense that right side to a single logarithmic term. So in other words, this is 2 terms. We need it to be 1. So the way I'm going to do that is use the quotient property. So the quotient property has allowed me to rewrite it in a way where it's 1 logarithmic term equal to 1 other logarithmic term. They both have the same base. And so it's appropriate here to use the one-to-one property. But again, in this first step, I use the quotient property of logs. And then here I'm going to use the one-to-one property of logs. And that's going to give me 5 equals 10 over x minus 4. I multiply both sides here by x minus 4. And then I divide both sides by 5. I get x minus 4 equals 2, or x equals 6. Let's test that answer, which is always a good idea when you have these complicated equations. So again, I'm going to use change of base. So that's log of 5 divided by log of 2. So that's this decimal value. We should get the same one on the right side if our answer is valid. So that's log of 10 divided by log of 2 minus log of 6 minus 4 divided by log of 2. and we see the same decimal in both cases. So our test has validated our answer. Another thing to be conscious of, you remember the extraneous solutions we used to encounter in radical equations? The same is possible here. If I plug a value in and the result is a negative argument, extraneous and invalid solution. So again, something to be conscious of. All right, let's look at this one.
Do you mind to go back to the work for that one?
Don't mind at all. I'm assuming it's this last bit, Shanika.
Yeah.
Finally getting down to the business of solving equations. We analyzed graphs, we learned properties all through this chapter. Now finally we're doing the real business of mathematics. You good? Okay. All right, so another one here, perhaps the most challenging thus far. Log base 5 of x squared plus x equals log base 5 of 20. So in this case, I have a single logarithmic term on both sides already. So I can immediately apply the one-to-one property. So same base, one term on each side. It's good that I can immediately apply the one-to-one property of logarithms, which gives me, if I subtract 20 from each side, gives me this, which is going to factor pretty quickly. I've got x plus 5 and x minus 4, which gives me x equals negative 5 or x equals positive 4. And we'll just make sure that works. Negative 5 squared is 25, plus a negative 5 is log of 20, log base 5 of 20, yes. 4 squared, 16 plus 4, 20. Yes, both of those are valid solutions. This is challenging because it requires you to remember logs and their properties, and also how to solve a quadratic. Sometimes when a problem draws from several levels, it's more of a challenge. Questions about this one? Okay. So here's one for you. Here's the hint. You're going to have to use laws of logs on that right side. Give that one a go for me. And remember what I said about solutions being invalid. this case, it's the product plus sign. So you'll multiply here. So you'll divide.
Okay.
It'll be x times.
Okay.
That's fast. How do you get rid of this one? That would be log base 3 negative 3. Any answer ever makes the original argument negative. It must be disconcerting. So that was one. And if you had this on a quiz or a test, this would be one of the distractor answers. So make sure to test your answers on that logarithm. Now be careful with this one because this plus sign means it's product property, not quotient property. So we're going to multiply here. So it's x times x minus 2, which is just a simple difference. You'll only need to rewrite that right side of the equation. You're welcome. All right, I'll start working through this and you compare what you've got to me. So this is product property. Meaning we multiply, it's because of this plus sign. If this were a minus sign, we would divide. It's a plus sign, so we multiply. One-to-one property gives me this. Distributing the x gives me this. Setting equal to 0 gives me this. Factoring gives me this. Which gives me two answers. However, if I try to plug in that negative 3, I would have a negative argument for the logarithm. The negative 3 is therefore an invalid and extraneous solution, and only x equals 5 is valid. So just make a mental note of where you stalled if that happened. And know you'll have to get through that sticking point before the quiz or the test. In this case, a test, which will be tomorrow. Already prepped. All I have to do is hit assign. All right. So these look pretty innocuous. Just 3 symbols. But if I had given you this problem a week ago, you would have had no means by which to solve it, except for trial and error. So now we have the logarithm. This variable is in the exponent. So if a variable is in the exponent, your answer is to take both sides as the argument of a logarithm. You remember in previous problems, we exponentiated, took as the exponent. Here we're going to take as the argument of the logarithm. Again, the yin to the exponential's yang. So what undoes exponentiation? The answer is the logarithm of that same base. So this is taking both sides as a log. And I'm going to choose whatever base is the exponential's base. So this would be x, and I'll rewrite this using the change of base property so I can estimate it in my calculator. It's about 1.77. See how easy the logarithm makes those problems. All right, questions before we continue? Okay. So e to the 2x plus 1 equals 8. Once again, I need to use a logarithm, take both sides as the argument of a logarithm. What base is appropriate here, Kobe? Well, you can't use 1 as the base of a logarithm. 2. Think carefully. What is the base of my exponential? E. And so what do we call the logarithm with base E? We're going to take both sides as the argument of a natural log. And once again, that will undo this exponential and rescue that variable. I subtract 1 from each side. Divide by 2. I get this expression, which they want us to estimate to the nearest hundredth. So natural log of 8 minus 1, and then divided by 2. It's about 0.54.
Can you explain real quick how you went from the natural log of e 2x plus 1 to the natural log of 8? That down real quick.
Yeah. So remember that the logarithm undoes the exponential. And so for any log, the log base b of b to the x power equals x. So whatever that exponent is, just drops out. And in this case, that exponent's 2x plus 1.
Oh.
So because the natural log is base e, and this is an exponential with base e, then this property applies. It's a good question, Clay. It's a tough concept. Seems easy, but the underlying mathematical structure is very complicated indeed. And again, you're just going to have this mental resistance to the logarithm. I can't explain it. I don't know why it happens, but it does seem to be every year. Kids just have this cognitive barrier when using the logarithm. Your brain's just averse to it. You ever not like something, but you don't know why you don't like it? You ever read The Telltale Heart by Edgar Allan Poe? The old man with his vulture eye, who was so kind to the protagonist, and yet so hated. The logarithm's like that. It's a kind old man. It's trying to help you, but you just hate it. All right, here's one for you. 4 to the x power equals 9. Give this one a go. If you get stuck, I'll come around and help you. Excellent. So that's like he's trying to get it takes. Matt, rewrite that with change of base. So you should get it. Use the one. Yeah, my 4 is essential. Whatever the exponential is, it's also. Make sure you consider that in both cases, this is log base 4.
Isn't that just confuse me? And
Yeah.
the last one is that really special.
Yeah, because it's a natural log.
Yeah.
But it is the log base e,
Yeah.
and that's power of e. So this is power 4, meaning we should use the log base 4. So write a little subscript 4 right after it. Yeah, okay. And that would just become x. And then that's, if you use the change of base rule, log of 9 over log of 4. And that's what you can do in your calculator. All right, so Colby, tell me what you got here just in terms of the logarithm.
Log base, log base.
Excellent. And what was the decimal approximation for that, Mason?
1.58.
Excellent. Okay, any questions about this? Sweet. Look at more challenging one here because we've got multiple bases. What happens when you've got more than one kind of base? What the heck kind of logarithm do I use now? I could use 3 or I could use 2, but when you have more than one exponential base and no single logarithmic base will solve it in one step, it's advantageous to use either the common log or the natural log. You'll see me default quite often to the common log because it's what I did in college. I just got used to it. Most PhD professors will default to the natural log. Not sure why, but it does seem to be conventional. There is no reason to choose one over the other in this case. I'm going to take both sides as the argument of the common log. That's because I have more than one type of base. Once you have chosen the common or the natural log, taken both sides as the argument of the log, you can now use the power property of logs to move those exponents out as coefficients. From here, the algebra gets a little messy, but this will probably be, these first couple steps will be what challenges you. Everything after this you've done before. All right, so let's distribute. So that's 6 log 3 times x minus 3 log 3 times x. And the x is not part of the logarithm's argument, so make sure you understand that's the case. Use parentheses if you need to. Let me show you what it would look like with parentheses, because that'll probably be more clear. So that's 6 log 3 times x minus 3 log 3 times x. And that's going to be equal to 4 log 2 minus 4 log 2 times x. So that was just distribution. Now, in order to solve this, I need to get everything with an x on one side, everything without an x on the other side. So here I've got 2 terms that I can actually simplify. This is 6 times log 3 minus 3 times log 3. So the result of combining these 2 like terms is going to be positive 3 log 3 of x. And then I'm going to add this to each side. Now I'm going to factor out that x. Parentheses no longer so necessary. Now I'm going to divide away this messy thing here. So there's my answer. Do they want us to approximate? Yes. So that is 4 log 2 divided by 3 times the log of 3 plus 4 times the log of 2. So that's about 0.46. me put that on. So again, everything down here you've done before. It's challenging, but you've done it. This is the new stuff. All right, ladies and gentlemen, that's the end of chapter 3, part 4. Next, I'm going to briefly discuss chapter 3, part 5, but I'll make a new video for that.